This video is all about how we can find the equation of a quadratic when given some key information about it. We know that the general equation of a quadratic is y equals ax squared plus bx plus c. And we know that we can write it in factorised form to help us to find the roots of an equation. So if we know what these coordinates here and here are, that helps us to know what these are going to be. And we know about completing the square, so writing it in this form, if we know about the turning points, this coordinate here. It's important to state, though, these are currently written in their most simplest forms, and actually there may be a number at the front of both of those like that. And we're going to see how important that is in a minute. So, couple of examples when we know about the roots. Both of these equations here have the same roots. They both have a root of 1 and 3, which makes me think that I could write down the equation as x minus 1 and x minus 3 in its factorised form. This is from the root of 1. This is from the root of 3. But there could be a number at the front there. That number might not need to be there. It might just be a simple 1, but it might need to be there. And we'll see that in a second. So I'm going to expand these brackets out. So I'll get x times x is x squared. X times the minus 3 is minus 3x. The minus 1 times x is minus x, and the minus 1 times 3 is 3. Collecting up those like terms, and now expanding each of those, multiplying each of those terms by the number a. If we need that a, we might not need it yet, we'll see in a second. Now I'm comparing my y-intercept here with the y-intercept of the blue graph. And we can see it is 3. So 3a would equal 3. So that a, in my case, in the blue case, is just going to be 1. So actually, I didn't need that a for the blue line. However, for the green line, let's have a look at that one now. We can see it has the same roots at the beginning, so I'm going to start off the same way. Y equals x minus 1 and x minus 3. But there could be a number at the front, so I'm going to put that there. Now expanding those brackets in exactly the same way. And collecting up the like terms. And expanding. And now comparing the y-intercept of the green graph, 3a equals 6, which is telling me that a has to be 2. So therefore this is going to have to be 2, this is going to have to be 2, and this is going to have to be 2. So the equation of that green graph is y equals 2x squared minus 8x because of the 4a times 2 plus 6 because of the 3 times 2. So that's the equation of the green graph. So key thing from this is having the roots alone isn't enough to tell you the full equation. It will tell you the basic form, but there could be a number at the front there because there are lots of ways I could draw a quadratic that has roots of 1 and 3. And having that a at the front allows you to uniquely identify which quadratic we're talking about. Now, with these next two examples, there are no roots. I've not been given any information. In fact, there aren't any roots at all. But I have been told about the turning point. So let's do the purple line first of all. I know that the turning point of the purple line is 1, 2. So in completed the square form, that's making me think x minus 1 all squared plus 2. The x minus 1 here is coming from the plus 1 there, and the 2 is coming from there. But, just like in the previous example, there might need to be an a at the front. So, same idea. I'm going to expand those brackets. So I've got the x squared. I've then got the x times the minus 1, so minus x, but there'll be 2 of those, so minus 2x. And then the minus 1 squared is plus 1, plus the 2 over here. Multiplying each of those terms through by a now, I've got the a times x squared, the a times the minus 2x, the a times the 1. And just like I did in the previous examples, I'm going to compare the term on the end here, my y-intercept term, the constant term, with the y-intercept there, and I can see it's 3. So a plus 2 equals 3. So a has to be 1. So this is 1, this is 1, this is 1. So the purple line is 1x squared minus 2 times 1x plus 1 plus 3. So that's the equation of the purple line. Whereas with the orange line, it has the same turning point, so I'm going to start off in a similar sort of way. I'm going to start off with the y equals x minus 1 all squared plus 2. Again, because of the x plus 1 here, so the x minus 1 there because of the plus 1 x coordinate. And the plus 2 here because of the plus 2 here. But just like before, there could be a number at the front there that I need to work out. So expanding those brackets in exactly the same way as I did before. And now comparing my y-intercepts, the 5 is equal to a plus 2. So now a is 3 in this example. So I need to replace a 3 here, here, and here. So the equation of the orange line will be 3x squared minus 2 times 3x plus 3 plus 2 is 5. And so that is the equation of the orange line. And so, just like before, simply having the turning point isn't enough to uniquely define the curve. I could increase the value of a to have a quadratic that looks like that, or even start having negative values of a that have the same turning point. So we need that a at the front in every example. Final type of quadratic that we might need to work out the equation of is where they haven't given us the roots or the turning point at all. In this example, I've been given the random points 1, 7 and 3, 5, I have quite usefully been given the y-intercept though, so I can replace my c with 5 because I know that's my y-intercept. So I'm going to do that first. Now the next thing I'm going to do is use one of these coordinates. I know that when x is 1, y is 7. So if I substitute that in, y is 1, so y is 7 rather, when x is 1. So I've just replaced 1 here and here, and I put 7 here. And I've got a times 1 squared, or a times 1 is a, b times 1 plus the 5, and I'm going to subtract 5 from both sides. And that's telling me that a and b added together is 2, but there's not a huge amount more I can say about that yet. I need more information. Luckily, we do have some more information though. I also know that y is 5 when x is 3. So just like I did a moment ago, I'm going to do that same process. The y is 5 when the x coordinate is 3. Three squared is 9, so 9 times a plus 3b plus the 5. I'm going to subtract 5 from both sides, which will give me 0 equals 9a plus 3b. And dividing through by 3, just to make the numbers a bit easier. 0 divided by 3 is 0, 9a divided by 3 is 3a, and 3b divided by 3 is b. And again, there's not a huge amount more I can do at that stage. But notice now, I do have simultaneous equations that I can solve to work out what a and b are. So if I were to do the second equation, this equation here, take away the top equation, or the other way around if you prefer, doesn't really matter. But I'm going to do the bottom equation, take away the top equation. So I'll have 0 take away 2. I'll have 3a take away a, which is 2a. And I'll have b take away b, which is just 0. So 2a is equal to minus 2. So therefore a is equal to minus 2 divided by 2, which is minus 1. And now I know that a is minus 1. I can substitute that back in here, or here if you prefer, it doesn't matter. I'm going to substitute it into here. So 2 equals minus 1 plus b. So b is equal to 2 plus 1, which is 3. And now I know that a is minus 1. And I know that the b is 3. So therefore, I've managed to work out the full equation of this quadratic. So this is quite a lot longer process than the previous two examples we've just done. We could have used this method with the previous examples, but it takes longer. And that's because we were given these random points at the beginning. If we know about the roots or the turning points, then we'll definitely use that example because it's much quicker. If we don't, we can use this method.